evening, everyone. I hope that you are safe. I'm Jad Al, Project Coordinator of A. And I'm going to talk about the internship program that we made in January of this year. To start, here's an image for the BAU students that went to Egypt. For the first week, we studied about TechLog, that is a software developed by Schlumberger that enables you to perform both basic and advanced interpretations of all wellbore data types, including log, core, images, photos, and 10 sections. This is an image of our luxury office during the workshop. And here's another when we took our certificates for the TechLog software. In the second week, we learned about Prosper software that is specialized in production engineering. We learned to plot the inflow and outflow curves and obtain the operating pressure and flow rate, and also know how does the operating point value changes with the value of the parameters. And here's another image when we took the Prosper certificates. Over here, at the third and fourth week, we went on a geological field trip and visited the great companies as Baker Hughes, Corex, Schlumberger, Pico Energy, NAPSCO, and Rizapomp. In our geological trip, we traveled for 8 hours from Al Maadi, where we lived, to Al Jalala mountain, as you can see on the map, on these arrows. And we saw faults, different types of rock, and talk about their geological time. And this image shows the doctor explaining about the rocks during the trip. And now I will show you some of the images of the companies that we visited. Here we were at Schlumberger. Over here at Baker Hughes. And this is an image for Pico Energy. And this slide shows the ending ceremony where we took our third certificate. I had a great day with the OPA board members and our instructors. Another internship program this summer, but we postponed it due to the circumstances. And now OPA is planning to develop an online internship program. And over here, I would like to show you the astonishing view from our apartments. Over here, you can see the Nile River and the pyramids on the right, as you can see. Thank you. And Omar, the stage is yours.
And now I would like to welcome Dr. Rami Aloush to start his session. Welcome, Dr. Rami.
All right. Good evening, everybody. Your time. It's still morning here in the States. Thank you all for joining. It's a very big number. I didn't expect, so hopefully I have something meaningful and beneficial for all of you today. Our session today is titled, as you already know, it's machine learning in the oil and gas industry. I would like to look at this session as an eye-opener. The field is very, very big and it's very, very dynamic. It's all about just getting the idea that there is opportunity or that the machine learning is applicable in the oil and gas industry. And then you can take it from there to further develop yourself and dive deeper in this very, very large field. And so try to just cover very little or basic things, but the whole idea is to be an eye-opener for you and for you to realize that there is a very big chance and opportunity to apply machine learning in the oil and gas industry. So before we dive deeper, just give a very brief intro about myself. I'm not sure, I'll try to be slow. I know the slides take time to reflect. So my name is Rami Aloush, as you know by now. My background is mainly petroleum engineering. I have a bachelor in petroleum engineering from Phoenicia University in Egypt, after which I worked in the American University in Cairo as a teaching assistant. And then I moved to Saudi Arabia, where I got my master's degree from King Fahd University. And then I worked with Saudi Aramco as a part-time consultant assistant on a big project, actually. And after I finished it, I moved here to the States, the United States, to pursue my PhD, which I'm doing right now, working in the Center of Innovation for Flow Through Porous Media. So when it comes to the machine learning, I have couple of publications. We published different papers on the applications of machine learning, specifically the artificial neural networks. We have some applications on the well logs, on the geomechanics, some for the well testing, and some for some reservoir properties and characteristics. I have a nano degree as a machine learning engineer from Udacity, a couple of scholarships from here and there. But of course, I'm still learning, and we are all do, because, as I said, the field is very dynamic and it's changing on like a monthly basis or even weekly sometimes. So our session strategy, so that you have your expectations set, we will try to cover the very, very basic approaches in the artificial intelligence and machine learning. Like we can spend months actually if we are to explain everything in details. So I'm just touching the surface here to give you an idea, like I said, to act as an eye opener for you, so that in your fields or on your study or in your senior project, you see that the opportunity. You know what? I have this data, so I might be able to apply this technique or that technique, but you will have to do the search and you have to study on your own, but just you have that concept that, okay, how can I apply, or what could be transformed in ML or utilize the machine learning. This is the whole purpose of the session. We'll try to correlate some of the technologies that we cover with some of the challenges in the oil and gas industry, and explore some of the case studies through very recent papers. Like even my papers I didn't implement here or incorporate, because like they are a couple of years old. So all the papers, we'll touch 3 papers, all of them published this year. Like they published last month, one of them February, and the other is April 2020. So I try to give you like the very recent advances on the kind of applications that are happening for the machine learning in the oil and the gas industry. Another point that why this session is important, some of you were mentioning the reduction in the oil prices. And we don't know if it will rebound soon or fast or never, whatever. The idea that this is a golden opportunity for you to start to broaden your knowledge. Many companies will start maybe do cost reduction or something. So they will try to automate things, or try to utilize the machine learning and artificial intelligence more. So it's a very good time or important time for you to broaden your knowledge and to try to get into this field, because it will very much shape the future of the industry, and it's already doing this. But now, especially with the cost reduction and the low prices, this will be more and more important. So it's a very important time for you to jump on this chip. So we'll start with some trends, just try to get the terminology right, and for you to understand some of the terminology. It's very tricky when it comes to the terminology, because they are very much used interchangeably in many fields, and many people confuse them with one another, even specialized people. And sometimes it comes to opinions. People disagree, so each one is naming something different, and sometimes it comes to lack of knowledge or whatever. So we'll try here to get the big picture, the things that most people almost agree on, and this is the differentiation between 3 or 4 main terms. The first one is artificial intelligence. So the artificial intelligence is trying to make the programs have the ability to learn and reason like humans, ability to react. So this is a very broad, and here comes like the science fiction movies and everything. So we are not very much in the artificial intelligence when it comes to the actual application. The actual practical applications actually is of this subset of machine learning. So we are not interested in making robots talk or anything. Our main idea is that to try to make the machines do the tasks that humans already do, but with much more efficiency and accuracy, and of course time saving. So when we say machine learning or ML, it's when we try to make the algorithms or the machines learn without being explicitly programmed. So we don't have to write the exact code and tell the machine what to do. No, the machine can on its own learn from the data. And we will tab on this in a much more details. And then we have the deep learning, which is again a deeper subset of the ML, which refers to the ability of utilizing a lot of data. So the deep learning is a subset of the machine learning. We adapt neural network, but it utilizes huge amount of data. So to emphasize more on this, as I said, when we try to enable the technical system to have this experience concept. So we as human, when you try something more and more, you become good at it, you do it better. So this is what we try to make the machine do. We try to give this ability to the machine to be able to gain this experience and to learn on its own from the data. So the more data you give it, the machine will be able to extract the relationship, extract the patterns in the data, and then she will be able to act upon them. A very basic example is like if we have some images from a camera, and then you teach the machine, this is a good image, this is a bad image, this is a good image, this is a bad image. And you do this for a very, very, very long time, for a very long amount of data, I mean, the machine will be able to do it on its own. So, okay, so now if this is the concept of machine learning, where comes this neural nets or the deep learning, which actually some people like classify the deep learning as a subset of neural networks, which are just bigger networks. But before going into this, again, let's stick to the difference between when we say machine learning, we just try to teach the machine. So the deep learning comes with the ability to consume large amounts of data. If you see this chart here, you can see usually with the traditional learning algorithm, you start giving data to the algorithm, and the algorithm is actually learning. Its performance is increasing. But at a certain point, however much data you give it to the machine or to the algorithm, it cannot improve much. It has hit its maximum capacity or performance. But with deep learning, because there are too much ability to observe or absorb information, so the more data you give it, the more the system will be able to learn. So that's the key difference between the relatively new branch of deep learning and the traditional machine learning in general. Another way or another importance why the machine learning is very crucial at this time, as John Naisbitt did, one of like futuristics or people who can predict the trends, he says you are drowning in information and starving for knowledge. So we have a lot of information, we have a lot of data, we have multiple sensors, smart fields, we collect huge amounts of data each second, but then our ability to process this data and comprehend it and be able to draw knowledge and take decisions based on this data is what we are starving for. And as humans, it's very, very limited for us to be able to handle like the big data, handle millions and millions of points of data. Like usually if we have like 100 points, we plot them in Excel or something, and we try to draw conclusions or patterns. But now with the big data, we are drowning information. We have huge amounts of data, per second, literally coming from fields, from wells, underground, on the surface, and so on. So we are not able to catch up and process these data. So here why the deep learning is very crucial part at this time, because we have a lot of data and we are not able to process them at a proper pace, and we need the help from the machines to do this. The best way I usually explain the traditional programming versus machine learning is these two simple images. Because many people ask me, okay, we have already been using the computers to do the tasks for us. Like this is since like the 40s or something. So what's new? The concept here that what we have been doing with the machines is what we call traditional programming. As you can see on the left image here, so usually we have the data and we have the rules that governs this data, and we are just using the computers to execute these rules. So we know x equals 1, and we have a rule that y equals x multiplied by 2. So the computer can conclude that y equals 2. And if we have this data, y will equals 4, and so on. But the computer will be able to do it on a much, much faster pace. A very good example of this is the reservoir simulation. So theoretically, the reservoir simulator, when the computer will be able to make a reservoir run of like millions of cells, actually you can do it by hand. And I have did it. Like my master's degree, I programmed a complete reservoir simulator from scratch. And to verify that my simulator is working properly, I have to solve the simulation problem by hand. And it was like 3 cells, right? And it takes like 3 days for me to solve it by hand for 3 cells. So imagine running a simulator for like a million cells or something. So it's a very hard. So the computer is making it faster. But again, by the end of the day, we know the rule, we know the information, we know the equation of state, we know the wave equation, all the equations that governs the flow through porous media, and then the computer just makes it faster. But now in this field or in this time, we have these huge amounts of data that we don't have the rule. So we have the data that we gather from the sensors, and we have the answers. We have the reality, we have the production, right? But we don't know the actual rules. Why our production today is more than yesterday? Okay, we have all these hundreds of readings from all our sensors, but we are not actually sure what is the relationship between them. And here comes the machine learning. So the machine, you will give it some data, you will give it some answers, and the machine will be able to deduce a rule. The machine thinks the rule is this and that. And here comes the concept of learning process. So you keep giving data to the machine and it will learn from it. So how does this learning happen after all? We have three basic terminology, and then we'll cover the process itself of the learning. So the terminologies are very simple. We have what we call the data set, the features, and the model. And these are you will hear them a lot, so it's better you know what they mean. So a data set is just data examples that contains the features. And when we say features, it's the important pieces of information that we need to cover. So if you need to teach it something, you have to have the data that you are sure capturing this thing. You can, for example, you cannot just give the machine all the data about oil reservoirs and you expect the machine to learn about gas reservoirs, right? Because the characteristics or the features of the oil reservoirs are different from the gas one. So you need the data or your data set to capture all these features, to capture all these pieces of information. So if you want to teach it about gas reservoirs, you give it data reservoirs. If you need a machine that can learn about oil reservoirs, you need to give it data with all these features, data about oil reservoirs, data about gas reservoirs, and all other kinds. So once you have this data set and you are sure that it has the features or the pieces of information that you care about, then you try to make your model. And your model is the actual representation. It's the relationship. It's the rule. So if you know, like if your rule is that the relation between X and Y is this model is what governs this information. And here is the distinct difference, because usually we know this rule. Like usually you know the relationship between the reservoir pressure and your oil flow, whatever equation you use or whatever model. But when it gets very, very complicated, you don't actually know the rule. Here comes the machine learning that will have a model on its own. It will generate these rules or deduce these rules. So again, what is the process? Like, what do we actually do in reality? It's very simple. We collect these data in the first step, the data collection, and then we start the data preparation, because usually the data, you have different data from different sources, some of them from like downhole, some of them are from the wellhead, some of them in the production facility, whatever. So you collect these data, you prepare them to be in a unified format, or make sure they have the features that you need. And then step 3, the main step, is the model fitting or the model training, where you create the actual relationship. And after that, you start the evaluation. Did this model perform well, or it performed bad? So based on this evaluation, we try something called hyper tuning. We try to change these parameters of the model to make it perform better. And then we go in this cycle again of fitting and evaluation, and so on. We keep trying until we are satisfied of what the model has learned. So this is in a written format, just for your reference. We collect the data and prepare it, train it, or fit it, the model, evaluate, and then keep going in this cycle. So now let's get a little bit deeper. Like now we understand the general idea, but let's get some practical approach of applying the machine learning. So there are many classifications. And as I said, this is very dynamic. So here I just showing you the very basic early classification of the algorithm or approaches used in machine learning. The main 3 or the most famous are the supervised learning, the unsupervised learning. People have, like in many categorizations, there is the semi-supervised learning, but it's not like one of the core, so I'm skipping it here. And we have the reinforcement learning. We will go through each one of these as brief as we could, but again, while trying to give you the idea. And then we will start with the case studies and see how these concepts are being applied in the oil and gas industry. But someone might ask, so where's the neural network? We keep hearing about this neural networks, so we don't see them on this graph. And I'll come to this later after we explain these approaches and why they are not included in this graph. So let's start with the first concept of a supervised learning. A supervised learning is the most thing that makes sense. It's very simple, very clear. It's all about like how we learn in school, but instead of students, we have robots learning. We give them examples. We give them the data. You know what? This is the question and this is the answer. This is the question and this is the answer. That's simple. It's very, very simple. And that's why it's called supervised. We are controlling the learning process of the machine, or we are teaching the machine. So the goal here is to learn the mappings or the rules or the relationships between some of the inputs and some of the outputs. To give you a related example that, okay, so what? Like what? The first very simple example would be like if we have our input as well logs. Like in the introduction, we were talking about TechLog. So TechLog, actually this one, the project that I worked on in Saudi Aramco, and we have the publication on that specific example, that we have some well logs and we need to extract information from them. So usually you have the petrophysicist that uses this software, try to interpret these logs and know what they understand or what they mean, So they try to understand these logs and interpret them. We can do this so this petrophysicist, he spent a lot of time learning. He saw a lot of examples, he saw a lot of well logs until he can easily, once he sees this log, this resistivity with this saturation or whatever, he can tell, okay, this formation is this or this formation is that. So this is a very simple example. So we can do the same with the machine. We can give the machine a lot of well logs, and for each section we can tell, okay, so with these given logs, actually the lithology of the rock is this, or the geology in this region is this, because we know this. Now, some more critical or complicated examples may be like something like the rock strength, for example. We don't have this direct relationship. We don't know for sure if these logs exist, the rock strength would be like this. We have some inference, but we have from experience, or we can know from the type of rock and so on, but we cannot have an exact number, or we don't have high confidence. So we can do this by machine learning. That we let the machine extract some rules that we don't know about. They are not very clear to us. So they describe the relationship. And to do this, as I said, we have to provide a lot of information to the machine. And this information is called labeled data. By labeled data, we mean that it's data that we know the answer to. So, for example, we give the logs to the machine, and we already know what type of rock this is, or we already know the strengths, the rock strength, and we give it to the machine. So machine will know the problem and will know the answer. So we give this information to machine for a set of data, some size of data, but it's a limited size, of course. And then the machine can have a rule, and hopefully the machine can generalize this rule to be able to apply to any data. So in the future, we don't have to do anything. We just give the machine some logs, and it will tell us our rock strength, although we don't know it. But the machine has learned it from the labeled data we have given to it. So as I say in the second point, it will be able to output a prediction for the rock type or rock strength or whatever that we have learned it. A critical point here, just a side note, is that we have to be aware of the type of data that we give to the machine. Like if we need a machine to be able to extract all type of rocks, we cannot just give it like limestone, because if we give it sandstone in the future, she will not be able to recognize it. So we have to have an unbiased data or reliable data or representative data that captures all the features or all the important information as we emphasized before. Again, reliable data is the source or the main core of the machine learning algorithm now, and this is why we call the data is the new oil. It's very, very expensive now. The data, it's all about data, because this is what makes companies stronger than others. Now, to do supervised learning, so what do we want the machine to do? As I said, we needed to be able to know or predict something. And this prediction comes in very, very two famous forms. I'll touch on them very quickly. The machine would be able to do classification or regression, and you might have heard these terms before. So when we say, it's very, very simple. So when we say classification, it means the machine can determine the class of a certain property. For example, it will say, okay, the rock strength is low, high, or medium, just in general, like such as a category. But for the regression, the machine actually will give you an exact number. So try to have a real world scalar from this. So these two graphs hopefully explain it better. So the top one here shows the classification. So you have a certain input. Let's say this is two values for a certain log. So this is whatever, resistivity and saturation. I know it's not necessarily make sense, but you have these inputs, you give it to the model, and the model will classify it. It will, okay, this data good or bad, or this rock is limestone or carbonate, or this strength is high or low, whatever. It just have a class, like, or a category where it finds, where it fits the data. For the regression, it's a little bit different. You give it a number, and then it can give you an estimated other number. So for example, you give it the saturation or the resistivity, and then it can tell you, you know what, the rock strength is 100 or a 99, or the tensile strength or whatever. So it gives you a number. So just about the expected output of the machine, this is the main difference between a classification and a regression problem. Now, the second type of the machine learning approaches or algorithms is the unsupervised learning. And unsupervised learning, of course, it's harder because we are not explicitly teaching the machine. We don't have this labeled data. We just give the machine only input data, bunch of data, there is no labels, and then we hope that the machine will figure it out on its own. So as you can see, just hearing it, it's really, really more challenging. Just imagine, like what I try to emphasize here, usually people don't believe this is doable, this can be done. Like, how come like you just give it a bunch of data and you are expecting the machine to figure out what to do with it? A very good example of this is like we as children, if we give a child a bunch of like toys and they have different colors, with time it's very expected that the child will be able to separate them, each toys with their own colors. Like my daughter did it like 100% on her own. You just give her some things with some colors and she just start separating them with a matching color. I didn't teach her anything. And this is called the clustering problem. And this is very famous for the unsupervised model to do. So it's kind of a knowledge discovery. We are not sure actually what relationship is there or how this data could be classified or could be clustered. It's unlabeled data, but the machine can start to extract patterns. Like, okay, all of these are big and all of these are small, so just put the bigs alone and the small alone. Or there are very, very big varieties of approaches. Some of them are dimensionality reduction, latent variable model, anomaly detection, which also makes sense. Like you have everything is like within some range, and some data are outliers. They are completely in a different range. So without telling the machine anything, she can detect the anomaly or the outliers, and she can do this. I'll just touch here on the main application again for the unsupervised learning, which is the clustering problem. So as I said, like my daughter example, so you just have some, as you can see in the graph on the left, some original data, and then the machine will cluster them. So these data are together, this data together, this data together, just some kind of clustering without actually any effort from our side, like by just having some subgroups for them, or some by finding some characteristics in them. The other, again, I'm putting these for your reference because they are relatively big list of things. The association, the ability of the machine to uncover the rules between the data, or the anomaly detection that we called about something unusual. The machine can extract it on its own without explicitly teaching it, and that's why it's unsupervised. Or the dimensionality reduction, which means the machine can extract the characteristics or the features that are just important or that makes a difference. The machine doesn't have to get like you give it a 10 feature, and the machine tells you, you know what, all these 8 they actually don't change the output by any means. It's all about only these 2 features that control the behavior or control the flow or control the problem and so on. So this is the second type of machine learning, the unsupervised. The third one is the reinforcement learning, and this is very famous in the gaming concept or the gaming industry. So you see, if you just downloaded a mobile game on your phone, for example, and you start playing it, you don't know anything. You don't know how to play this game. We as humans, what you do, you start like moving forward, and then you have something like very green and very cute, and you try to touch it, and then you die, right? Usually, like you avoid the red things, but the green things are good. But okay, this game is different. So the next time you play the game, you will try to avoid these green things. That's it. You don't have any reason. You were punished when you touched the green things, but you were awarded or your score increased when you touched the red ones. So from now on, you will avoid the green ones, you'll touch the red ones. Simple, right? This is how humans think or behave. And this is the exact concept we use with machines in the reinforcement learning. We call the rewards program, or the positive and negative feedback, or reinforced behaviors. It's used actually in psychology as well. So you try to motivate or reward the positive behavior, and you try to give a negative feedback for the bad behavior. And the machine learns, so she keeps trying, and you can see online videos on YouTube like machine learning learns to play Mario or different kinds of games. So all the targets, she wants to maximize the score and avoid the score. So I will not touch deep because I'm not aware of much applications in the oil industry of this type of learning, but it's just, as you can see here, you have your agent that you are trying to teach, and you have your environment that agent is interacting with. So the agent will make a certain action with the environment, like jump or move forward or move backward, while we are talking about a game. And then the environment will reply with a reward and a state. So when he touches the environment, its state changed or its state stayed the same, and then it has a reward, a positive or negative reward. So the agent will keep learning. Okay, when I did this action, my reward was bad, so I need to try another action to get a better reward, and so on. So this is the general concept of reinforcement learning. And as I said, I am personally not aware of much applications in the oil industry, so I just skip it for now, but I give you the general idea or concept. So before we moving forward, I want you to be very, very aware or watch out that whatever source of information you see, make sure that we have tens of thousands of machine learning algorithms, and hundreds are coming every year. So just yesterday, I got this snapshot from actually Wikipedia, which is not a reliable source of information, of course, but just for comparison. So you can see, we just say the main ones are supervised, unsupervised, reinforcement, and you can see there is self-learning, feature learning, sparse, dictionary, whatever, and so on. Like Wikipedia is listing 10 of them. And if you go like a more reliable source or a book, they know what, these 3 are actually under this one. They are actually only 5 or 4 or whatever. So my whole idea here is to try to give you this concept that the namings are a lot, the approaches are a lot. Each one, like as you can see here, the neural networks are not even classified as an approach. No, it's a model. Other people know they classify it under supervised learning, and as we will discuss. So it's some opinionated field because it's already developing, but I don't want this to discourage you or, okay, oh, my information is wrong. No, you understand the concept, you understand the basic, you understand that each algorithm has these main 3 components. It has a representation, how to represent it mathematically at least, and you have the optimization, how this model is improving itself, and then you have the evaluation, how to evaluate this model and know if it's doing a good job or not. So now, as we explained all the 3, let's go back to the neural networks. And as you see here, the neural networks, some people call it artificial neural networks because they are based on the same concept of our brain. So the neural networks, the difference between neural networks and the deep learning is just the number of neurons. We will know what does neurons mean now, but just as a concept, the only difference between neural networks and deep learning, which we hear a lot, okay, what's deep learning and what's machine learning and what's neural networks? I hope this graph summarizes it. So neural networks are one of the approaches to machine learning. Many people classify it under supervised learning, but it's a structure, it's a model. It could be used with different approaches. Some people use the neural networks for reinforcement learning. So you improve the neural network by reinforcement learning. Some people use the neural networks with supervised learning. So they have the neural network, but then they teach it what to do. So it's a supervised learning. So just don't get yourself discouraged or distracted by the terminology, just understand the big picture. So from neural networks, so the deep learning is basically just a neural network, but with many, many, many neurons. It's a very big neural network. And that's why it accepts, or it can absorb a lot of data, as we see in the first graph. The more data you give it, the more the performance improves, because it's a very big and it can absorb a lot of information. So how does a neural network learn in the first place? What does absorbing information mean for a neural network? The main concept, I'll just touch the very, very basic concept of a neural network, which was introduced in the 50s, which is the perceptron algorithm. The neural networks are very big topic, huge topic. There is a Stanford course on the neural networks. It's 2 semesters almost just to learn about neural networks. So in this like 1 hour session, I'll just touch base on the concept that a neural network is just a very simplified model of the human neurons, and it has an activation function that decide if this neuron will have an output or not. I'll try to have just one graph with a very simple concept to explain this, but as I said, it's a very big topic. So here we can see if we have this problem, we need to draw one line to classify these two data sets. So now it's kind of, we are trying to teach the machine, like we try to create a rule that when you see this data, you can separate them by this rule. So if like, let's say these are dogs and these are not dogs, for example, so we can just have this line. One approach of drawing this line is like, okay, we will measure the distance like between this. We need this line to be as close to this as possible and as close to this as possible, to be exactly in the middle. This is a very rough concept. So once we have this line, we can draw this line with a simple line function. So we have the x multiplied by a constant, which we call here the weight. So this is the general function of a perceptron, which is actually a line function. It's x multiplied by a certain weight, and we add b, the constant, or what we call the bias, right? Very, very basic. Now, what's an activation function? So an activation function is what uses this perceptron or this classifier to make a decision. So our decision here is if this is a dog or not. So we need output to be 1 or 0. 1 if it is above 0, like it's above the line, and 0 if otherwise, anything else. So this is an activation function, a very simple, very basic activation function. So this is the very core concept of a neural network, right? It's a perceptron concept. You give it some input, and it will give you a basic output based on the value of the weight and the value of the bias. This is the very basic concept, and I will not go any further, but you can see this very basic concept can be applied here with this is a complete feed-forward network. This is one of actually my paper used this model. But as you can see here, we have these inputs. We can have different inputs, and each one of these sends the input to all these hidden layers. And inside these hidden layers, we have this concept of perceptron. So you have this input, you make a decision, and you send your output. But as you can see here, it's not just a linear relationship, it's a network. This input is connecting with all these hidden layers, and this one again, and this one again, and all the outputs are connected together, and then they might be averaged or whatever based on the kind of activation function. But the whole concept is the same. You have some inputs, you have some outputs, and you have a simple rule inside that governs the relationship between your inputs and your outputs. Now, when you have hundreds of these connection points or neurons, you will be able to gather a lot of information. So if the input is higher than this, but lower than this, but between this and this, but depending on the type of input, if this is a will log, and this is a different will log, and this is a different will log, you can see there is no one equation that governs. It's a collection of rules that gets built inside this network, which makes out or which defines at the end the neural network or the machine learning algorithm you have. So this is one of the rules or one of the algorithm, the very simple concept, but hopefully this opens your eyes, like it's not magic. It's very simple mathematical equations that being applied for many, many, many times with different inputs and different outputs, and then it gives a unique relationship to your model, and that's why your model can learn. The more data you give it, the more these equations, these W and B, can change within the equation until you reach the best numbers to give you the expected output. This is the classical neural network or the very basic artificial neural network. There are more advanced ones namely the CNN and the RNN, the convolutional neural networks, which are used for image classification basis mainly, because imagine if you need your network to understand an image. As you know, the image actually is a bunch of pixels. Each pixel is a number from 0 to 255, and you have a lot of them. So a neural network that will be able to deal with images would be accept like 1 million pixels or something. So these numbers, dealing with them with like a very simple neural network is very hard. It's very hard to capture the pattern. So the convolutional neural network, they use the convolution concept, which you might have studied in mathematics, to be able to extract the feature by reducing the number of pixels to the pixels that are just important. And it has a very, very smart way of doing it. But again, we cannot dive into details, but I'm just trying to open your eyes that you can, if you are interested in dealing with images, you can study the convolution neural network, and we have a case study on this as well, because I try to make the case studies as broad as possible, from the upstream to the drilling downstream, as I showed you in the strategy slide. Another one is called the RNN, or recurrent neural network, and it's very important when you have to build decisions based on previous information. For example, like the neural network I showed you, you have one input, you get one output, period, done. But actually, many problems, again, I'm not aware of very advanced implementations of these in the oil industry, although there are some, is when you need to make decisions based on previous information. Like Google Assistant, for example, when you speak with it, you don't just tell her hi, and then she gives you an output. No, you would say, hi, Google, what is the length, for example. So these are 4 words, and she will interpret each word, but she will not take a decision. It will wait for the next input, because each word is an input, for example. So it builds its response based on previous information, right? It's not just one information in, one information out. No, it will build history of information. And because that's why it's very advanced and very complicated, but it's very critical, like for the documentation and voice recognition. Again, for a document, you cannot just translate one word in its place. You have to understand the context of the whole sentence, for example, to be able to translate. So again, many different types of neural networks, and once these networks are very big, they become deep neural networks, and this is like the current boom, I can say, in the industry, but hopefully you understand the concept of it. So now, once we covered this, let's dive into some case studies. Again, we are just touching bases. These are all pretty advanced papers. You have the citation down here. You can go download them. So this paper, the first paper, is just published this month. It's from Stanford, actually. Pretty advanced paper, but pretty smart, actually. So the target of this paper, they were trying to predict the multilateral inflow control valve profile. So, you know, once you have a multilateral drilling, you start to install these inflow control valves, and then you can have hundreds of configurations, how to set these valves, what values to set them to give you the best performance, because they have high dimensionality. They can be set in many, many different ways. And again, we as humans, we don't have a certain rule, like how to set the valve for this specific well or for this specific multilateral well. So you have very, very high number of variables, of the inputs, of possibilities, and you don't have a certain rule. So they were looking, can we use machine learning to try to deduce these rules for us? Maybe the machines can see patterns that we cannot see, and they can optimize it. So this is the workflow they are using to optimize the life cycle of any newly drilled well. So what they will do, they will do the actual drilling, and then they start gathering the production and gather the data, because the configuration, the better configuration will be judged by the better production, of course. So that's why they have to have the production data and control. And then once they have this production data available, they start to feed it to the machine learning and try to start to predict the flow and see if this prediction is matching the production they have. And based on this, they can charge optimizing the inflow control valve configuration to be able to have a better production profile. So as you can see, this is the very general concept. Now, if we stop here and together try to think how to do it, right? This, like, now we know some people did it, but if we are to think about it, how can we do it? Because to be able to teach them the model, we have to have huge amount of data, huge amount of configurations, right? And actually to get the actual production, this production to be reliable, actually you need like to wait like maybe 3 months for each configuration, right? To see, okay, when I modified this, I got this output, and then you wait again, and then you wait again, and you need like hundreds or tens of thousands of data points for the machine to actually learn. So what they did, they used simulation. Here comes the funny part. So they did a reservoir simulation where they install the valves. As you can see, they have 3 valves, they have the production, and they have 2 case scenarios. They have the first case, they had a homogeneous reservoir model, and the second one, they have a heterogeneous reservoir model. So they have the reservoir models, inside them they have the ICVs, and then they can generate very, very big test cases. So they run the test case with certain configuration, get the output, and then run again, and until they have a good data set. If you recall the terminology, the first thing is to have a data set that captures the features. And here, to be able to capture multiple features, they didn't just do one model. They have two models, one of them homogeneous, one of them heterogeneous, because they want the data to have different features, right? Once they have, as you can see here, they have these 3 valves that we saw in the simulation, and then we have the sampling that they are taking from each valve, and some of them they used as training data, and some of them they used as a predicted output or unseen data. And this is a very important concept. Like when we try to do the learning or the fitting of the actual model, we don't just give the model all of our data, right? We don't make it all training, because if we give it all the training data, we expect the model to learn all of these data, and then we cannot test it. We cannot do the actual evaluation. If you remember step 4, we cannot judge if the model did a good job or not. So what we do, we have our data, but we don't give it all the model. The seen data is seen by the model. Seen here means seen by the model, and unseen is unseen by the model. So we give the model our data, but we hide some data from the model. We don't give it to him. And we make him learn, we do the training and validation on this data, and then we try to test him. We still have some data that the model know nothing about, right? And we start to ask the model about this data and see his performance, if the model or its performance, he is not human, and see if the model is able to predict this data or not. It's a very, very important concept, and very it's used with all types of learning and all types of algorithms. So here, this is their neural network, and this is the one we talked about. So this one, it has a shape, we call it tapered, fully connected neural network. Fully connected means that each neuron is connected to all the neurons in the second layer. We call these layers, right? So we have 4 hidden layers. This is the input layer, this is the output layer, and these are in between them, they are the hidden layers. So we have 4 hidden layers. They are fully connected, but they have only one unbiased or one biased neurons. If you pay attention, you can see this one at the top, they don't take input. They are just taking output. So it's called biased because it doesn't get affected by the input. It just makes a decision, just gives an output. So they have 4 hidden layers, and they have the activation function as the real. Of course, we said there's different types of activation functions and optimization functions and optimization algorithms. So we are not going into this. This is the actual science, but here we are just covering the big picture, as you can say. So here are some of the results. We're not again going into details, but I'm just showing you that basically they were able to test on both cases, the homogeneous and the non-homogeneous, and with more data, which is very expected. These simulation runs, more simulation runs means more data, right? And you can see this is here the loss. Usually the loss is what the machine got wrong. So you try to reduce the loss and you try to increase the R2, which is like the correlation, so it has a better. So you can see with increasing information, with increasing simulation runs on the x-axis, your y-axis is improving, either for higher R square or for lower loss on the square root. So this is the first case. As you can see, it's the conclusion from this case is pretty simple. As you can see, with only 10 ICV settings, they were able to have a very strong neural network, which has a very high 95% of accuracy, and it could be applied in the future to predict the best configuration of the inflow. So this is one example for the utilization of the machine learning in a case. And the idea, like someone was asking about the senior project. So senior project, we usually do simulation. So this could be a very good idea that you can extract a lot of cases, a lot of data from the simulation and apply a machine learning. And as you can see, this is something that just got published from Stanford. So it's a very, very good and novel approach, and learning this at a senior project level will be something fantastic, actually. The second case study we have is the identification of downhole conditions in sucker root pump using deep neural network and genetic algorithm. So I have this example here because it has a different concept that we can combine different learning algorithms. So the genetic algorithm is, I believe you maybe know it. It's one of the very famous optimization algorithm. It's not directly a machine learning algorithm. It's an optimization algorithm. So they use the genetic algorithm and optimization algorithm to try to improve the neural network. Because as I told you, the neural network, you have to choose the number of neurons. You have to choose the number of layers. You have to choose the values of the weights and biases of each single neuron. So it's a lot of information. This is what we call the network tuning. Try to adjust all these numbers. So doing it by hand or by trial and error might be very hard. So here it was a very smart idea that they used another optimization algorithm, the genetic algorithm. This is actually published from Cairo, Dr. Al-Bambi, AUC and Cairo University. Again, it's published this year when they try to utilize this. So the idea here is you have to understand the sucker root. What does the sucker root do? What is the dynamometer? What is the card? You have to have this domain knowledge. And this is why I try to have the examples as variable as possible. But it's a very important message for you to understand that don't just go and say, I want to apply machine learning in the petroleum in general. No, you have to look at your domain. Because the more you understand about your problem and about your domain, the better you can get a proper model or a better solution. Machine learning will not just create something from scratch for you. This is a very important concept. So here, this is the structure they had. As I said, they have the dynamometer, the card points as inputs, and then they do the feature extraction, normalization, whatever data processing that needs. Again, this is different for each problem, for each domain. And then these classifiers is a combination between the machine learning, ANN, and the genetic algorithm to have, together they are working to do the prediction. Again, without going into details, this is the general concept. So here you can see this is the classification. So for them to be able to use this classification, they have to have an expert, because now for each case of these cases, these cards, they look different for each one of them. Each shape means a different problem that we don't know about. We are not domain experts. So if this is high and this is low, this means you have gas, otherwise you have a pump failure, otherwise you have blah, blah, blah. So it has there is a big different scenarios or cases that could be the problem, and then they have to get an expert to classify them for each one. Can you imagine total number of cars? 6,000. So they manually classify the 6,000, and this is what we call the labeled data. So they are labeling the data. They get someone expert. He does the analysis for these cards, but now the knowledge from this expert is transferred to our model. So when we have a new card, we don't have to bring the expert. We can just bring the model that has been trained. So they combine this optimized neural network and the genetic algorithm to get the ANN structure. Also, the feature extraction is a big deal. As I told you, it's different for each case. So here they use the EFD, one of the very famous descriptors, the elliptical Fourier descriptor, to be able to get the features. Like they analyze the signal from, if you recall the Fourier expansion and everything, so you analyze the signal. And as you can see, for this case, the signal is different, the input is different. So it needed a different kind of data preparation. That's why the second step, data preparation, is very important, data engineering. And it's a complete rule in many, many companies. It's called data engineering, how to change the shape or the structure of the data to be able to be used in a neural network. So just having this, you cannot use this in a neural network. What is this? But for them, this step, the feature extraction, was very specific. They had to use the EFD to be able to extract the feature, and this data or this signal was able to be fed into a neural network. The third problem, again, very slight, touching base very quickly. I know I'm running out of time. Is classifying the shell shaker. Now it's a drilling problem. So in the shell shaker, you have the cutting volume with the shapes of the return. Like, I believe you know this maybe better than me. I'm not a drilling person. But the idea here is using the CNN. This is why I had this example here. So what they do, they have a camera at the shell shaker, and they would take this image, decode it, have the frame, and start supply this to a machine, a model. So we have the trained model, they do the training, and then this trained model, once it has a frame, it can decode this frame and have the result, what is the best cutting volume out. This is, as you can see here, so this is the camera feed. You can decide the cutting board detection, and then you can see the volumes of the shell shaker and analyze the image. And this is using the CNN. As I told you, when it comes to images, usually we use the CNN. So I tried to have a very varied examples. Here's the results for them. Usually we explain the results using something called a confusion matrix. This is the confusion matrix. What it does basically, it says, okay, this is what the prediction. So this is the actual label, that the actual data, because this is labeled data, right? We train the model, so we give it some data, and then we wait for it to extract the data or predict the actual value. So here you can see when it was heavy, he correctly identified it as heavy for 75% of the cases. When it was extra heavy, he was very good at identifying the extra heavy at 99%, for example. But when it was light, it was always identifying the none as light, for example, and so on. So from here you can judge the accuracy of your model, know what categories, what areas it performs better than what, and you can judge your expectations from your model. So I know I'm running out of time. I'll just conclude with this final thought that any machine learning algorithm, the general practice, are very simple 5 steps in an infinite loop. The first thing and the most important is understanding your domain knowledge, the prior knowledge, the goals. You know what you have at your hand, and then the machine learning comes to help you, right? You don't just imagine I learn machine learning without knowing my domain. If I'm working drilling without actually understanding the drilling, understanding the problem, the machine learning will not help you there. But you have a certain problem, and then you understand your problem, you understand the task, but then you believe machine learning can make this task faster, make it smarter, make it requires less people. And that's why companies will be investing more, because they need less people to cost reduction. And that's why it's very important for you to jump and be able to provide input on this side. Once you have this domain knowledge, you start with the data integration, selection, cleaning, processing. As we saw in one of the examples, it's very critical. Sometimes your data is in a shape that's not ready to be dealt with using machine learning. So you have to do some processing or some selection or whatever to prepare this data for your model. Then you start learning the models and apply them. And here, usually, you try different models with different approaches. And then once you have these different results, you start to evaluate them, see what is better, remove what's not working, and invest more in what's working. And you can then start over with deeper knowledge or with deeper understanding or with better data selection and so on. It's an infinite loop of learning and improving, and it's ongoing cycle. You cannot just say I'm done. It's an infinite cycle. So with that, I'll conclude my presentation. Thank you so much. Hopefully you learned something, and I'm available for your questions. So we'll go take the questions through the chat, I believe, right? I'm not sure how to catch it. Okay. Maybe some of the moderators might jump in and help me, I guess.
Yes, you can take the questions from the chat, please.
Okay. So it's jumping very quickly. I'll take from Alia. This is the first one I catch. Do you think AI and ML can effectively be used in real-time identification of downhole problems during drilling? Yeah, so as you saw from the shell checker example, actually there was a paper. I'm glad you asked it. There was a paper, but I thought it would be very long to include more case studies. But they have a paper which used geosteering actually. So they were trying to optimize the geosteering while drilling by reading the data. So they were reading the logging while drilling, and they were analyzing the logging while drilling to be able to guide the geosteering. So it is possible, and it is being done. So yeah, again, I'll try to share as many papers with you and references as I can, but feel free to search the domain. It's going crazy, very fast. Thank you all. Okay, I'm not sure if I should. Okay, is Python language adapted in ML in the oil and gas sector? So Python, as you can see, Python is the standard language for machine learning and data science right now. There is R for the data science, of course. But yeah, and again, this will not be a judging factor from my humble opinion. Like, if you understand the concept, you understand the domain knowledge as a company, and you come to me, okay, I'm working with R, I'm very bad with Python. Actually, like, it will be funny, because once you know Python, you know R in no time, and vice versa. And once you understand the concept, the actual language is not a problem, because once you get into a company, actually each company has what we call its stack. So the company will be using a specific provider, maybe using Microsoft Azure, for example, or using Amazon AWS, or using Google Cloud. Every company will have its own solutions, but you don't have to learn them before you join the company. You can, of course, but this will not a judging factor, because the company understand that if you're good at what you're doing, you understand the concept, just learning a new stack, learning a new platform, learning a new language is not a big deal. But understanding the concepts, the knowledge, the domain knowledge, this is what matters. This is from my opinion. Can you recommend any books for machine learning oil and gas industry? I'm not aware actually of a specific book because it's relatively new. But what I can really highly recommend is the SPE. They have just launched a new committee, the digitalization and machine learning. I'm not aware of the exact name. Sorry. I'll share it with you as well with the organizers, and they will share it with you. So weekly, they send you the latest trends in the machine learning and oil and digitalization and oil and gas industry. It's my main source of information. It's very good. You can really rely on it. And I believe there might be some books, even if there are books, they will be announced through this newsletter from SPE. So it will be a good source for you. I'll share it with you. Please take notes, the organizers, because I might forget. So everything I say, I will share. Please write it down and remind me. I want to ask about the Internet of Things. Under what category do you classify it? So the Internet of Things, like there is a very good picture, but I don't have it. The Internet of Things, you can put it where it captures everything, because the Internet of Things has very reliable part on the communication and being able to run on the edge and being able to run on low power and so on. So it has a very big part on the electricity, communication, and so on. And then as an Internet of Things device, you can use anything. You can use a CNN. I have applications that use CNN on a Raspberry Pi, for example. Or you can use a simple classifier or audio detection, for example. So as an Internet of Things, you don't have to classify it under machine learning. Like actually machine learning is just some of the aspects utilized to be able to have an Internet of Things project. You use machine learning as a part of it, but then you use communication and use electricity, electronics, and so on. So it's not, it doesn't have to be under the machine learning, if I am to say right. Okay. What kind of computing horsepower would you need for real-time decision-making, like in-road bounding exam? That's a very good question. So as I said, it's very, very highly dependent on your application. Like for example, in that sucker rod example, actually the sucker rod, I don't believe the sucker rod was a real-time. Like the real-time was like for the CNN, for the shell shaker. If you are on rig, you actually have a power. You have like the company man facility and everything. But this is becoming less and less critical problem. Why? Because the advances in the models and algorithms, Google just open sourced something called MediaPipe. You can look it up. It's a very new way actually of writing models and machine learning models that it's very, very fast. It can run on mobiles or on. When we say the edge, it means like very small devices with very low power and low capabilities like ARM core or whatever. So this is becoming less and less of a problem actually, because the infrastructure, the companies are investing a lot on these lightweight, very fast, efficient inference models that work pretty well. Again, what do you think to check overfitting and how to avoid it? And very good question, Sam. So the overfitting is when our machine memorizes the data for anybody. Like when we say that our model is overfitted, that means we give it data, but then the model remembering this data, right? And then when he sees new data, he doesn't recognize it. Again, like it's not that technical. If we have like a deep course or something, we would have dived in codes and in much deeper terminology. But just the simple quick answer to avoid overfitting, you try to change your training and testing ratio. Like if you're giving your model 90% training and then 10 for testing, and then the model keeps overfitting, you try maybe give it like 70% training and 30 testing. So you're actually reducing the data you are showing to the model, hopefully to avoid overfitting. Now, even with this, if you're still getting overfitting, that means your actually data has multiple dimensionalities that are actually duplicated. There is a pattern in the data. And this is very familiar if you try to generate your data using an Excel sheet, for example. If you generate your data using an Excel sheet, there is an actual formula that you know about, right? And then the model can detect this formula, and then whatever you do, it will be 100%, it will be overfitting. So another way, there's something called data augmentation. You can use data augmentation, and you can try to apply dimensionality reduction on your data before, like in the step of data preparation. you start to apply one of the data reduction techniques or dimensionality reduction, where you actually reduce the dimensionality in the data, and this is most probably will avoid overfitting. The quantity of data produced could be too large to transfer to data sensors to be processed the right way, to convert the data sets, or maybe filter them before sending to servers. Well, this is again, Alia, is very, what I can say, is very application specific. Like, what do you mean by data? Because some of the data, like for example, for the images, like for the CNN example we saw with the shell shaker, when you use when you use images, most probably what we do, we reduce the size, like 64 by 64 pixels or something, or 120 maximum actually. Another way, we convert it from color to grayscale, right? So by this we remove actually 2/3 of the data, because you know a colored image is three layers, red, green, and blue. So we remove 2 layers, and then we have just 1 layer of grayscale, black and white. So this is one way of processing the data in a way that still captures the features for the model to learn, but reduces the size and the amount dramatically.
Dr. Roumieh, I think we passed the time by half an hour, so maybe we can send you the other questions and you can answer them maybe by email.
Okay, sure.
Okay, now thank you, Dr. Roumieh, for this amazing session, which delivered very new information for me personally, and I'm sure for everyone else.